online or offline? Okay. Is it connect ಆಗ್ತಾ ಇದೆ? ಅವ್ರ ನೆಟ್ವರ್ಕ್ ಇಶ್ಯೂ. ಓಕೆ. So, welcome Professor Malini Joseph to the conference. I welcome you, sir. Professor Malini Joseph.
Yes, good.
Oh, thank you for your response, sir. Confirmation. Okay. So now I am happy to introduce Professor Malini Joseph to this gathering. Those who have joined for this talk online or offline mode. Professor is working in Department of Mathematics, University of Iswantini, Uganda. So his area of research is applied mathematics, and he has done his graduation, Bachelor of Science with Education Honors, graduated second class, upper division, mathematics and economics as the majors. After completion of bachelor's, he has did postgraduate diploma in mathematical sciences at efficiency analysis of 2 basic control measures in malaria prevention. His research title and majors are mathematical sciences, African Institute of Mathematical Sciences, South Africa. Next, his PhD thesis title is Mathematical Modeling of Cancer Treatments and Role of Immune System Response to Tumor Invasion at as majors as applied mathematics at University of KwaZulu Natal. And so he has visited a number of countries as a fellow, namely I mentioned very few. Visiting lecturer at this one, visiting research fellow at University of Sydney, and with task of carrying out research, visiting research fellow at the Mathematical Institute, University of Oxford. All are visited with related to his research, and honorary research fellow at Durban University of Technology, with task as this one research profiles and supervising masters and doctoral students. Postdoctoral and course of research, apart from research, he taught the papers with the titles as Population Dynamics and Epidemiology, Advanced Differential Equation, Computational Methods, Differential Equations, Probability and Statistics, Calculus Part 1 and Part 2, Introduction to Numerical Methods and other branches of mathematics and applicable to the real world problems. He published a number of research papers in reputed journals with various impact factors of SCI, and very few, one or two I am explaining for our students to get the motivation. With Professor P. Dubey and G. Melinje in 2024, editorial Mathematical Modeling of Diseases and Population Level and Cellular Level. So publisher Frontiers in Applied Mathematics and Statistics, a very good reputed journal. And I am inviting this Professor Professor Malinje Joseph to address his talk, sir. Thank you. You are welcome, sir. I request you to present your presentation, sir, to continue your presentation, sir. Okay.
All right. No, thanks very much. Can I perhaps first request that you mute your microphones, because when Professor Godwin Ogunadi was presenting, there was an echo. So I don't know if you could mute your microphones. I'm thinking that 2 people in the room are possibly logged in. Yes, now I don't hear the echo. Perhaps again, if I could ask one of you to unmute yourselves and just confirm if you can hear me, then I'll start. But don't forget to mute yourselves again.
Yes, sir, we can hear you, sir.
Thanks very much. Thanks very much. So thanks for the lovely introduction. My name is Joseph Malinzi. I am based at the University of Eswatini. Eswatini is a very tiny but beautiful country here in Africa. It's sandwiched by Godwin, could you please reduce your volume that side? Because I can overhear myself. Okay. So Eswatini is a small country sandwiched by Mozambique and South Africa. I would urge you guys that if you visit Africa, you may want to visit Eswatini. It's a beautiful country with hills, and actually it's the only absolute monarchy, I think, that's left in the whole world. I'm also an associate fellow at the Durban University of Technology in South Africa. Now, I've listened to Godwin's presentation, and this one is going to be completely the opposite. It's applications, it's not pure maths, but yeah, so that's the beauty of specializing, having different specialties. So today I'm going to talk about the combination of 2 oncolytic viruses, and I'll tell you what oncolytic viruses are. And the title of my presentation is Mathematical Modeling of the Synergistic Anti-Cancer Effects of Combining 2 Oncolytic Viruses. And in this case, we are going to look at vaccinia and vascular stomatitis. This work is a collaboration with prominent professors around the world. Professor Helen Bain is based at the University of Oxford. Professor Anotida Madvamuse is based at the University of British Columbia in Canada. Professor Amina Eladadi is based at the College of St. Rose in the US. Professor Rachidovki is based at Northwest University in South Africa. Professor Raruka Eftimi is in France. We've been doing this work for a while, and hopefully we can be able to submit some articles for possible publication in good journals. Allow me to start by thanking you guys for inviting us, for giving us the opportunity to talk to you about our research. I would like to also thank a colleague of mine here at the University of Eswatini. She's called Dr. Abida Dodmani, who actually first contacted me and asked me if I was interested in presenting some of the work that I do. So thank you very much. I wasn't attending all the talks, but whenever I would get time, I would log in and listen to some of the presentations, because this side, I mean, it being a Saturday and Sunday, and it being that for us we are presenting online, then you would be caught up with other things, and also the time difference. So yeah, but I can see that the conference has been well organized, so I would like to thank the conference organizers. I would like to thank all the participants. And so yeah, Maybe in the future, if resources are there, we would be glad to actually attend face-to-face as well. I would really be happy to travel to India for the first time. So thank you. Thanks to the Department of Mathematics, Karnatak University, and the Private Institute of Mathematical Sciences. Okay, so straight to the talk. It's reasonable to think that when you combine two drugs, let's say you want to cure pain, then you combine aspirin and Panadol, then the outcome of treatment is possibly going to be better than when you use either aspirin or Panadol. But of course, you won't take 20 Panadols, 20 aspirins. So there will be questions of how many of each of the drugs are you going to take to cure the pain. So there is clinical evidence that the use of oncolytic viral therapy as a standalone treatment in certain situations, rather, there is clinical evidence that the use of combination therapies leads to maximum therapeutic outcomes, okay? And of course, it's reasonable to expect that when you combine oncolytic viruses with existing cancer treatments, for example, chemo and radiotherapy, it would lead to improved outcomes. But of course, there would be so many questions that would be needed to be answered. For example, how much of each, like I said, how much of the viruses would you combine in order to cure the cancer? So things to do with toxicity and things to do with which of the treatment characteristics are more important. And by the way, some virus drug combinations have already been approved for use. They're already being used by patients. For example, there's a drug called Talimogen Lapahevec. I think it was approved way back in 2021 for clinical use. Now, how do oncolytic viruses work? You have a genetically modified virus. So oncolytic viruses are genetically modified viruses. Your poliovirus, your measles virus, your COVID-19, any virus, for as long as, it can be genetically engineered to directly lyse cancer cells, okay? Then that can be turned into an oncolytic virus. So an oncolytic virus surrounds a tumor cell, kills it, and makes copies of itself, okay? Whereas when an oncolytic virus meets a normal cell, there is no replication. And so when the the advantage of the OV over the advantage of oncolytic viral therapy or oncolytic viruses over chemo or any other treatments is that there is direct cell killing, and when it kills the cells, it directly targets only the tumor cells, and when it does so, it releases even more viruses. Whereas when you use things like chemo will only look for fastly multiplying cells and will end up destroying even normal cells. That's why I think if you've seen someone on chemo, you'd see that their hair follicles have fallen off and so on and so forth. The advantages of oncolytic viral therapy, like I said, there is direct tumor cell killing, there is modulation of the tumor microenvironment, and there is local drug response. Now, this study is based on an experiment by Leboeuf et al. In this experiment, they would have mice with cancer cells, and then they treated them with one virus called VSV and measured the progression or the number of tumor cells that remain with time. And then those same mice injected them with vaccinia, and then measured the number of tumor cells, and then treated them with the combination. And as you can see, these are two cancer cell lines. There is the HT29 and the 41. When you use VSV, this is the relative tumor volume that you have with days. When you use VV, okay, so VV slightly performs better in the HT29 cancer cell line. But when you use both, the purple here, VVD, VSV, you can see that you have a lesser number of tumor volume, or the tumor volume is smaller. With time, it becomes smaller. In the 41 cancer cell line, that's another cancer cell, maybe type of cancer cell line. When you use VSV, VSV this time performs better in the 41 cancer cell line. VV, so VSV is performing better than that, but the combination leads to lower tumor volume. And the survival times, as you can see, the combination of VV and VSV, the survival times are bigger than using the individual treatments. Now, the rationale of using two distinct oncolytic viruses is that they complement each other's shortfalls, and their genetic makeup enables them to be synergistic. So, as we have seen here, that the VSV performs poorer in HT29, but performs better here. And whereas VV performs better in HT29. So when you combine them, then you're actually going to lead to it's going to lead to a ping-pong oncolytic effect, as I will explain, with each virus aiding the replication of the other in the cancer cells. So the combination leads to a ping-pong oncolytic effect in a way that each virus enhances the ability of the other to replicate, spread, and kill tumor cells. Now, the aim of this study is to formulate, analyze mathematical models that combine two complementary and genetically distinct viruses, that's VSV and VV. We hope to propose new testable hypotheses about the synergistic effects of VV and VSV. And of course, we're going to have some qualitative analysis and some numerical simulations, mainly to characterize the transient and qualitative dynamics of the model, the long-term model solutions. So the questions that we hope to answer are: how do VV and VSV interact synergistically to affect tumor cell dynamics compared to individual effects? What are the long-term dynamics, and under what conditions can the combination of VV and VSV lead to tumor eradication? What specific testable hypotheses can be derived from the model predictions regarding the effects of oncolytic viral therapy? And how do different treatment regimens, for example, timing and dosage of VV and VSV administration, affect the dynamics of tumor growth? And of course, through sensitivity analysis, we are going to try and identify the parameters which drive the outcome of this synergy, or the outcome of this combination. Now, what we already know from the experiment is that when you give, so we have two viruses, VV and VSV. We are going to consider a scenario. Of course, both viruses aid each other in replicating, in increasing replication and lysis. But we are going to consider the situation which is observed in the experiment, that when you give VSV, it leads to the production of interferon alpha. Now, interferon alpha acts, inhibits the replication of VSV. Whereas when you give VV, VV leads to the production of a protein called B18R. The protein inhibits the replication of interferon alpha. I know that that's a lot for mathematicians, but that's as far as I could simplify it, okay? That VV enhances VSV growth by expression of a B18R protein, and in return, VSV expression of a fusion protein enhanced VV growth. But we are not considering this situation where VSV is aiding VV. We are considering a situation where VHV, vaccinia, is enhancing the replication of VSV by expressing or by producing this protein B18R. And it's this protein that inhibits the production of interferon alpha, which interferon alpha inhibits the replication of VSV. So without vaccinia virus, VSV fails to replicate in certain cancer cell lines, for example, HT29. The vaccinia gene product B18R enhances VSV replication in certain cancer cell lines, for example, HT29. Interferon alpha inhibits VSV replication. Of course, every model is based on assumptions. These are model assumptions. B18R protein of vaccinia virus binds to interferon alpha and inhibits activation of interferon-mediated signal transduction. The mathematical model is in the form of ordinary, nonlinear ordinary differential equations. Later on, we hope or we aim to extend it to PDEs to also look at spatial effects. The model has 7 variables. The mathematical model that we consider has 7 variables measured in terms of time. And these variables are densities of the uninfected tumor cells. You have the VV infected tumor cells, VSV infected tumor cells. You have a free vaccinia virus. You have a free vascular stomatitis virus. You have a B18R gene product and interferon alpha. Those are the units of the models. So what happens is that you have tumor cells, you inject VSV. VSV leads to the production of VSV infected tumor cells. VSV infected tumor cells lead to the production of interferon alpha. Interferon alpha inhibits the production of more VSV. Now, whereas when you give VV, VV leads to production of vaccinia infected tumor cells. VV infected tumor cells leads to the production of B18R. B18R inhibits the replication of interferon alpha. So with those assumptions, you have this mathematical model. You have the tumor cells growing logistically. That's the intrinsic tumor growth rate. That's the carrying capacity of the tumor cells. Then you infect them with VSV. This is VSV. VSV, so that's VSV, it's V2. VSV leads to the production of interferon alpha at C2. Okay? Of course, these are the VSV infected tumor cells. That is VSV, and that's the interferon alpha. And now, modeling wise, we propose this function B2C2, which I'll show you. And in this function, when C2 increases, this reduces the effect of VSV. But if C2 decreases, then this becomes big, and so the effect of VSV on the tumor cells will be big. Of course, you want to infect as many. So the synergy of these two viruses, we are considering only V1 aiding V2, VV aiding VSV. That synergy is modeled through the function beta 2 C2. Again, I'm going to ask I'm going to ask someone to unmute and say if they can hear me.
Yes, we still hear you.
Thank you very much. Thank you very much. The viruses, the tumor cells, these infected tumor cells they have no use, in the sense that rather they are not lethal anymore, so they wouldn't harm the tumor cells. They wouldn't harm the viruses. They are viruses themselves, perhaps I should mention that, and they have a lifespan. So the infected tumor cells and the viruses have a lifespan. These chronic delta functions, I included them here to approximate the initial giving, the initial injections of VV and VSV. But when we are analyzing the model qualitatively, I mean when you are finding the fixed points and the stability of the fixed points, of course, because you need an autonomous system, then we don't include these. These, I just put them here to approximate the initial times of injecting VV and VSV. And now here, when you give VV, VV leads, VV is the V1. It leads to the production of T1 and leads to the production of the B18R gene product. And this gene product reduces the effect of the interferon alpha. Of course, we have a set of initial conditions and restrictions based on the experiment. And by the way, we were able to set up several meetings with the people who did the experiment, and we asked them so many questions. Here is the function B2C2, and we assume that it's a decreasing function of C2. Okay, so when you have the bigger C2 is, the smaller your beta 2 C2. This is the data. This is an extraction of the data from the experiment, the relative tumor volume with time. This is HT29, and then this is 41. Okay, just the data. When the tumor volumes, when you use VSV, when you use VV, and then when you use the combination in this cancer cell line. This is the model fit to the uninfected tumor cells, to the number of uninfected tumor cells, to obtain parameter values with respect to that experiment. So because the problem is that if you pick parameter values from everywhere, then you would not be representing in a specific situation. Your study would be hypothetical. Here we hoped or wanted to try and use some values that are meaningful related to the experiment. This is a model fit to the relative tumor volume 41. Now, in this picture, I'm showing that it's actually possible that when you vary the times, the initial times that you are injecting your viruses, such that you don't give them to the patient at the same time, it's actually possible to optimize that time, the initial time of injection. So here, I think it was tau 1 VV. So you've given VSV, then you delay to give VV. And you can see that VSV tumor-infected tumor cell density, actually, if you delayed for 25 days, maybe it's not the optimum, but it gives you many infected tumor cells, which is actually what you want. If you check VSV itself, again, after 25 days, you have a bigger number of viruses that you're generating. If you delay to give VV, okay, by 25 days. Here, this is a proportion TU over the total tumor volume. And you can see that here, maybe the optimal one, this one you want it to be small, you don't want a bigger one. And you can see that here, maybe tau equals to 5 is actually the optimum. If you waited for 5 days, that would be the optimum time to inject VV. This is a primitive way of optimizing, or rather finding the optimal time to inject VV. The best way would be to write an optimization algorithm. And I mean, if there are students here or people who would want to try out such a thing with me, you may contact me. I'll put my email address in the chat. To write an optimization algorithm which would give you the best times to inject either viruses. The advantage of non-dimensionalizing a model, of course, is that you reduce model parameters and you bring them to a uniform scale of some sort, because some of the parameters are measured, all the parameters are measured in different units. Some are huge, some are small. So you would want to, put them on some sort of a fractional scale and also reduce the number of parameters. And so that's what we did. And actually, we also assumed a steady state approximation of Z1 and Z2, such that because the replication of Z1 and Z2 happens on a faster time scale, minutes or seconds, than this which is happening in probably hours and also being measured in days. So that's the steady state approximation for C1 and C2, or Z1 and Z2 in this case. And so this is the mathematical model that we end up analyzing qualitatively. Of course, we've measured, we've proved the existence of unique solutions, the boundedness of these solutions, the positivity, etc. But of course, once you can see that your functions are continuously differentiable, okay, and also their derivatives are also differentiable, usually you won't have any problems because they are smooth functions. Really, they are polynomials, so we are not going to encounter any problems, I suppose. Now, equilibria, you determine equilibria by equating these to 0, because you want to find solutions that are time invariant, solutions which do not change with time. And the reason why you're doing that is because you're actually looking at the long-term behavior, because after a long time, these solutions, well, maybe they could blow up, but in most cases, they converge to the equilibrium, to some steady states. And so we determine equilibria in 3 situations. One, we assume that we don't have VV, so that's a situation where you have one vaccine, where you have one virus, VSV. And in all situations, you have 3 steady states. You have a state where everything vanishes and it's always unstable. So such a condition where after a long time you don't have any of the cells is not plausible. You have a situation where the tumor cells grow to maximum size. And in this case, where there is no VV, it's stable if this condition is fulfilled. And then you have a coexistence steady state. This one is a proof. I think this is a proof for the existence of the coexistence steady state. Or rather, yes, these are the steady state, the coexistence steady state is given by E32, this here, where we've defined these equations where Y star is obtained by solving this quadratic equation and blah, blah, okay? Now, this one is a proof of the existence of this steady state solution. It's just a proof that actually the solutions to the quadratic equation are positive, provided that this condition is fulfilled. Without VSV, you have the same story. Without VSV, you have the same story, that you have a steady state where everything vanishes. That's implausible. You have a steady state where the tumor grows to maximum size. It's stable if this is fulfilled. And by the way, I want to propose a lemma that actually, if this condition is vice versa, because this, you have a solution space where this steady state is unstable, and where this one is stable when this condition is fulfilled. And so I would like to propose that actually, if this is less, if the opposite is true, the solutions actually converge at the coexistence steady state. And maybe someone can prove me wrong later. But same story for this, the case where you only have VSV, that if the opposite is true, then the solutions are going to converge at the coexistence steady state. And also for the full model, it's possible to obtain steady states. The coexistence one is hard to obtain because you have so many equations. I think probably you'll have an equation to the power 5, I don't know, to the power 3, which is hard to solve. So you'd have so many huge expressions, but you can obtain the zero steady state where everything vanishes, and the steady state where the tumor grows to maximum size. Same story, this one is stable if the conditions for VV and VSV are fulfilled. And still here, I would argue that if this is less and this is less, we shall converge at the coexistence steady state. Some numerical simulations. This is a situation where you have VSV only. These are the tumor cell densities, the infected Y2, VSV infected, and the uninfected tumor cell densities. You probably want this, not probably, you want this red one, the density, to go to 0. And this is after 200, and actually this time here is the rescaled time to say that 200 represents the 200 represents maybe, I don't know, 250 days, because time was also rescaled. And you can see that VSV actually, with the parameter values that were used, it's unable to reduce this tumor cell volume to 0. And also it fails to replicate. The number of tumor cells are not that many, the number of infected tumor cells. VV only here with the parameter values that we used, the VV is capable of reducing the tumor cell volume almost to 0, okay, in less than, in less than 2 months, okay. And here is the combination, that the combination actually does it in a much lesser time to reduce these tumor cell densities to 0 in a very small time. Like I said, the infected tumor cell densities are not harmful, so one should not worry about those. We carried out several numerical experiments. Here is just one of them to check the effect of the burst sizes. The burst sizes, the virus burst sizes are so when the virus surrounds a tumor, the bigger it is, the number of viruses that it releases is the burst size, okay? And so we can see that as we increase the burst sizes, as we increase them, these are rescaled burst sizes, so maybe 4 represents 400, I don't know. But then as you increase the burst sizes, and you can see the infected tumor cell densities are 0. And of course, as the burst sizes are this way, are small, then the infected tumor cell density grows to almost maximum. Rather, the uninfected tumor cell density grows to maximum size. This is global sensitivity analysis. We calculate partial rank correlation coefficients with respect to several variables and at several time points. This one, a partial rank correlation coefficient measures, it's a statistical measure. It measures the importance of, in simple terms, it measures the importance of a parameter. If it's positive, then that parameter has a positive effect. When you increase that parameter, it increases the variable. If it's negative, it would mean that it has a negative effect. So when you increase the parameter, then that variable is reduced. The bigger the PRCC in absolute terms, the bigger the effect of the parameter on the variable. So it's a sensitivity index of some sort, because, and it's a good measure because, for example, we also have things like local sensitivity indices where you calculate, so if I was to calculate the local sensitivity indices, I would get partial derivative of this in terms of whichever parameter I am measuring, let's say alpha. So it would be partial this, partial alpha times alpha over this. But then that would have the assumption that all other parameters, for example here beta 1, beta 2, etc., are fixed and only alpha is varying. Whereas with global sensitivity indices, it allows for all other variables, all other parameters rather, to be varying in a certain range. And so it's a good measure of telling you which of the parameters is actually most sensitive to a certain, with respect to a certain variable. So here it's after t equals to 5 with respect to the fraction of uninfected tumor cell density. And we can see that here the parameters which are most sensitive are, or the parameters that dictate the dynamics of the dynamics of the model are beta 2. This is the infection rate of the uninfected tumor cells by VSV. Beta 1 is the infection rate by VV. Then we have the carrying capacity. Obviously, the carrying capacity would have an effect because of this YU here, because these are tumor cells. Remember, we assume that it grows logistically with the carrying capacity K. And then another parameter is C star. C star, that's to do with B18R, the maximum value. I think the half-life of B18R has an effect. It will be interesting to find out why. Then at t equals to 20, almost the same story. Those are the parameters which are most sensitive. At t equals to 200, after a very, very long time, still same issue. Those are the parameters. But then the virus burst sizes then also have an effect on the dynamics. And so perhaps what that means is that you want to have viruses which are lethal, which have big infection rates. You want to have parameters which, rather you want to have viruses which have big virus burst sizes so that they can infect as many tumor cells and release many viruses. This was just to check the effect of synergy through the parameter lambda. Lambda is the lysis rate of interferon alpha by B18R. And you can see that as you increase that parameter, you have lesser tumor cells. So that was to demonstrate synergy. We also calculated some global sensitivity indices called SOBOL, but the SOBOL indices are not pro-SOBOL indices. Sobol indices only tell you the effect. They only tell you which parameter is most sensitive, but they don't tell you how the parameter affects the variable. So we have total indices and partial indices here, and here with respect to the total tumor cell density, still we have the infection rates, we have the virus lifespans, and we have the virus burst sizes. And so this tells you that with this combination treatment of combining two viruses, the most sensitive parameters are the infection rates, or the parameters that drive the dynamics that you want to actually control or look at, or when you're designing the drug, put more emphasis on their characteristics. It's the infection rates, it's the virus lifespans, it's the virus burst sizes. And then with respect to the infected tumor cell fraction, almost everything comes up to be sensitive according to the Sobol indices, but it looks like still the infection rates and the virus burst sizes are still taking the lead. What I find this to be, how this is interesting in the sense that the parameters which have appeared in the sensitivity indices as the most sensitive are the same parameters which appear in the thresholds for stability of our equilibria. So you have, for example, with VSV, you have the infection rate there and the lifespan of VSV. With VV, same story, infection rate there, and the virus burst size and the lifespan, same story here. I think we had the virus burst size, and then with the combination, again, the same story. I think that's what I have for today. Thanks very much for your time, and maybe, I don't know if we have some time for any questions. Thank you very much. Maybe you should unmute yourselves.
Thank you, Professor Joseph ji. So, any questions from the audience?
Professor,
Sorry, I did not hear the question.
Professor, thank you very much for accepting our invitation and grace the occasion for your wonderful talk. Hello?
Yes, I can hear
Hello,
you.
Professor. Thank you very much. No, I hand over to the session chair, please.
Any question? If there are no questions, so I am personally and on behalf of the conference, I am very much thankful to the nice presentation by Professor Joseph regarding to the his talk. So he has delivered system of ODEs and provided a very good theorem for the solution of those systems. So thank you, sir. Joseph, sir, thank you very much and accepting for our invitation. Thank you, sir. Okay.
All right, no, thanks very much. If anyone, maybe you can tell the participants if anyone has been attending the talk and they have any questions, they could contact me. We can have a chat later on. I usually don't like it when I present and and don't get any questions, but it would be nice to, to have further discussions. Thank you. And I've put my email address here in the chat. I'm putting my email address here in the chat.
Okay, sir, thank you.